Tangent and normal lines. In this video, you will see how to find the tangent and normal line equations at a given point on a curve, and how to find the horizontal tangents to a curve as well. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. There are certain things you must remember from basic algebra and geometry when solving for the equation of a tangent line. A tangent line is a line that locally touches a curve at one and only one point. The slope-intercept formula for a line is given as follows, where m is the slope of the line and b is the y-intercept. The point-slope formula for a line is given as follows. This formula uses a point on the line and the slope of the line, denoted by m, to calculate the slope-intercept formula for the line. Let's see how the equation of the tangent to a point on a curve can be found by differentiation. The slope of the tangent line is the derivative of f of x at x equals a. Let b a function. The tangent line to this curve at the point is given by the point-slope formula, where m equals f prime of a. Let's see how it works. Find the equation of the tangent to the curve at the point where x equals 1. In order to find the equation of a tangent, we have to follow the steps. Differentiate the equation of the curve. We rewrite square root as power to use the power rule. Substitute the x value into differentiated equation to find the slope. Substitute the x value into the original equation of the curve to find the y coordinate. Substitute the slope and the point we have just found on the curve into the point-slope formula to obtain the tangent line equation. This is the equation for the tangent line. Finally, check with the graph to see if your answer is reasonable. There is another important line. It is perpendicular to the tangent line and perpendicular to the curve. This is the normal line. In figure, we can see an example of the normal line. You may be asked to find the gradient and the equation of the normal to the curve. The normal to a curve at a particular point is the straight line, which is at right angles to the tangent at that point. That is, it is perpendicular to the tangent line and perpendicular to the curve. The slopes of perpendicular lines are negative reciprocals of each other. In other words, the product of their gradients is -1. Find the equation of the normal line to the curve at the point where x equals -2. Differentiate the equation of the curve. Substitute the x value into the differentiated equation to find the slope of the tangent line. The gradient of the tangent is 7. If two lines are perpendicular, the product of their gradients is -1, so we find the slope of the normal line. Substitute the x value into the original equation of the curve to find the y coordinate. Substitute the slope of the normal line and the point we have just found on the curve into the point-slope formula. This is the equation for the normal line. Finally, check with the graph to see if your answer is reasonable. There is one more important tangent line: horizontal tangent lines. Horizontal tangent lines are parallel to the x-axis. Horizontal lines have a slope of 0, and the slope of the tangent line is given by the derivative evaluated at a given point. So horizontal tangent lines occur where the derivative is 0, f prime of x equals 0. Find the points on the curve where the tangent line is horizontal. To find the values of x for which f of x has a horizontal tangent line, take the derivative of the function. Then set the derivative equal to 0. We can proceed by factoring the polynomial. So the roots are 0 and 2. Then we find the corresponding y value in the original equation to determine the 2 points where the line tangent to f of x is horizontal. Finally, check with the graph to see if your answer is reasonable. We will now discuss differentiability, that is, whether or not the derivative of a function exists at a given point. The derivative at a point exists when the limit at the point exists. There are 3 situations where a derivative fails to exist. When the curve doesn't have a tangent line because of a discontinuity. Look at the graph. The function is not continuous at x equals a. The limit of f of x as x approaches a does not exist. The graph has a sharp corner at the point. Look at the graph. This function is continuous at x equals 0. But let's try calculate the derivative at 0. Since the left and right hand limits do not agree, then the limit doesn't exist. Then the derivative doesn't exist either. A function like this with a corner not smooth would seem to have many tangent lines and thus many slopes. Function has a vertical inflection point. Look at the graph. In this case, there is a vertical tangent line at this point, but the slope is undefined, and thus the derivative fails to exist. There is a vertical tangent line at this point. The slope is undefined.